Okay, so part 2, we just concluded with the arc length here. We showed how to get the arc length when we're dealing with radians. We take the central angle in radians times the radius. We'll get right to it. When we're dealing with degrees, however, my old method works beautifully. All right, so here is a little bit of a physics type idea. We're talking about angular speed and linear speed, and this is referring to when we have a point, say for instance, oops, I want to fix that, hold on a second. Okay, if I have a segment from the center going off to the side on these circles, and I imagine that point revolving around like in a clock or on a, on perhaps a merry-go-round or anything that goes in circular motion here. There's two kinds of speeds. There's the speed that the angle at the middle is changing, but then there's also the speed that a point on the circle is moving. Those are referred to as angular speed and linear speed. The linear speed, the speed of the point on the circle moving, depends on the size of the circle. If I move this arc or this segment at the same speed I was moving the other one, so that the central angle is moving at the same speed, the point on the circle has to be moving faster. You can think of it as, imagine your car has two really big wheels on the back and two really small wheels on the front, and you're going 60 miles an hour, say. Which tire is actually moving faster? Well, the smaller one is, because it has to cover more, it has to spin more times in order to cover the same amount of ground. So linear speed is how fast the point on the circle is moving. We see that up here at the top of the slide. Angular speed just describes how fast the angle is changing. Well, the way I like to think about this, we know that distance equals rate times time. If I take this simple relationship and I solve for the speed, or the rate, I have speed or rate equals distance divided by time. So that makes perfect sense down here with the linear speed. Now, all I got to think about then is how far is the point moving? In other words, what's its arc length? Divided by how long it takes for it to cover that distance, the time. If I divide these two, I will have the linear speed of the particle on the circle as it moves around. Angular speed is similar, only instead of talking about arc length divided by time, I'm doing the central angle divided by time. So these are two types of speed that we're going to actually go ahead and calculate. So I've got an example here I took out of the book. This is a lawn roller. I guess it would be used if you had to flatten out your yard after it was all lumpy or something like that. This is a heavy drum that you pull with your tractor, and you pull it around the yard, and it flattens out the yard, makes it nice and smooth. The radius is 10 inches, and this roller makes 1.2 revolutions every second. So what we're going to do is we're going to find the angular speed of the roller, and also we're going to find the speed of the tractor that's pulling it. Well, that's a really clever question, because the speed of the tractor pulling it is going to be the same as the linear speed. So basically, we have to find linear speed and we have to find the angular speed of this drum. All right, so continuing on here, we have a 10-inch, like I said, a 10-inch radius, 1.2 revolutions per second. We're going to find angular speed and linear speed. So let's start with angular speed. Angular speed, we saw on the previous slide, is going to be equal to the angle divided by the time that it takes to travel that angle. So we have theta divided by time. So let's talk about that angle. If it makes 1.2 revolutions per second, and we know that each revolution equals 2 pi radians, I'm going to take 2 pi times 1.2. I'm sorry, yeah, times 1.2, that's right, I almost misspoke there. Well, 2 pi times 1.2 is equal to 2.4. So that's 2.4 radians 2.4 pi, sorry about that. And the time that it takes for that to happen is 1 second. So you could say that I have 2.4 pi radians per second. That's my angular speed. You could leave it like that. You could take 2.4 times pi and get a decimal conversion if you like, if you're more comfortable with that. But that is your angular speed. Now we'll go down here and we'll figure out the linear speed. This is the speed that the tractor would have to be going. To do this, we need to find the arc length. And we divide that by the time. Well, the arc length, remember the shortcut I showed you back here when we're dealing with radians, the fastest way to find arc length is down here. Take the angle times the radius. So we're going to do that. We already found that the angle is going to be 2.4 radians. That's our angle. So I'm going to take 2.4 and I'm going to multiply it times the radius of 10. Well, 2.4 pi, my angle, times 10 gives me 24 pi. So I'm going to have, change colors here, 24 pi radians per second. And I'm sorry, not radians. That's the arc length. That's going to be measured. The top is measured in inches. I'm sorry. So it's 24 pi inches per second. Now this one, because we're talking about a speed, I'm going to go ahead and divide. In my calculator, I'll take 24 pi, and we're going to divide it by times pi. And when you divide by 1, it ain't going to change it. So this is about 75.4. And this is inches per second. So that's a demonstration of how to find these two speeds, linear speed and angular speed. And I'm borrowing these problems here from our text. Here's another one using a clock. A minute hand, suppose, the book example uses the second hand, so I figure I'd use the minute hand. The minute hand on my clock happens to be 5 inches long. I'm going to determine the angular speed and the linear speed of the tip of the minute hand. So I encourage you to pause the video and resume it when you think you've got that. So we'll go ahead and do our angular speed. So we need an angle divided by time. Well, the angle in one full revolution, this is going to go 2 pi radians. How long does it take for that to happen? Well, with the minute hand, that takes 1 minute. Well, 2 pi radians, 2 pi, if you multiply it out, is approximately 6.28 is approximately what 2 pi is equal to. So I have about 6.28 radians per minute. That would be my angular speed. The book example uses the second hand, so they converted this to seconds, and it's slightly different. I encourage you to visit that. Down here, we'll look at the linear speed. Linear speed, remember, we need an arc length. Well, we know that we've got 2 pi radians in one full revolution. So the fastest way to get the arc length is to take 2 pi, that angle, whatever that angle is, and I'm going to multiply 2 pi times the radius of 5. That's going to tell me the arc length. That's going to tell me how many inches this thing is covering. And I'm going to divide that by the time it takes for that to happen, which I'm going to leave it as, 1 minute. So when we do this, 2 pi, and we're going to take that answer times 5, I get about 31.42. And this is going to be inches per minute. So that's how far that thing is traveling, if the radius of the clock is 5 inches. If the radius of the clock is bigger, well then obviously the linear speed increases. If it's smaller, it decreases. And one way to keep in mind, keep in mind that I told you at the beginning that there's approximately 6.28 radians in a full circle. And a radian is the angle formed by wrapping this radius around there. So it would make sense that there's about 6 times 5, or 31.42 of those guys in a minute. So that's a couple examples. This is going to be a big topic. You are going to see this on your test. You are going to see word problems involving this, and this is something you cannot ignore. This is not just the extra problems at the end of assignment. This is important. You have to be able to use this concept in the context of a word problem. And that could be a lot of things. Anything that spins around like this. Could be clock, could be a merry-go-round, could be sprinklers, could be tires on a car, could be a machine, gear, could be anything. And we're going to have to be able to apply this concept here. So some practice problems. We're going to go, and this will begin. I'm trying to be really, really selective here. Feel free to do more. You know, there's certainly more problems in the book. But I think beginning on page 255, I should have you do numbers 5 and 6. I think you should try number 9, something like number 9 and problems like it. You should be able to do that. I'll throw in number 13. I'm going to have you do 17 and 18. Let's see here. I think you should be familiar with the quadrants. So you should look at numbers 27 through 30, 31 to 34. Check those. I'm not going to assign them, but check those. Make sure that you're aware of how to do those. I am going to have you do 45 through 63 odds. Those, I think, are something that we need to do. That's the conversions, radians to degrees, degrees to radians. That's something that we absolutely have to be comfortable doing. You got to get quick and good at that as well. Now, in addition to that, I'd like to give you guys, try number 77. If you know how to do it, it's quick. And you can try 78, 79, and 80 if you need more practice there. That's not a problem. Let's see. I think I'll give you 85. Try that and problems like it. And then we're going to get to the important things, the word problems, 97 and 98. So we got to get this done. We're a little bit behind. We got to do some catch up here. So stay tuned, revisit the site, check it again. You will find something up here hopefully tomorrow, maybe possibly tonight, depending on my schedule and how much time I'm able to put into this. A new chapter, guys. Let's have a good one here, okay? See you guys.